team is going to talk about the Mathematics 3 PBL, which is about the function of the planimeter. Our team is conformed by Ricardo Flores, my name is De Jesus Gutierrez, and this instrument is called planimeter and is used for topographic projects and to calculate the area of irregular shapes. The one that we see in this image is used to calculate the area of irregular shapes. There are different types of planimeters. The one that we saw has a fixed end that is on the surface of the irregular shape that we want to calculate the area, and it has a metal tip that is used to scroll around the figure that we want to know the area.
Known information. The instrument is called planimeter. The instrument is used to calculate the area of an irregular figure. The instrument uses calculus and mechanics to calculate the area. The instrument has to be calibrated every time that it's used, and it uses trigonometry to find the area too.
The information needed to know is that we have to know how the instrument works. We have to know the mathematical principle or algorithm that the planimeter uses, and we have to know if the instrument follows the steps of the integral, and to know that if the results are the same as the ones given from an integral.
This time, our problem scenario is quite different but simple. We are not asked to do any calculations or to find a particular result. We are only asked to find the mathematical principle on which the planimeter works.
If an enclosed curve C is given in the parametric equations x equals x of t, y equals y of t, and z equals z of t, where t belongs to alpha and beta, the area is equal to the integral from beta to alpha of x times y prime dt, that is equal that minus the integral from beta to alpha of y times x prime dt, that is equal to 1/2 of the integral from beta to alpha of x times y prime minus x prime times y dt.
With a further analysis on our findings, we realized that we could have reached our previous results with the use of the Green's formula, which relates the integral along an enclosed curve with a double integral along an enclosed region. First, let's take a look on the Green's theorem. Let P of x and y and Q of x and y be scalar fields with partial derivatives on an open S of the plane xy. BC a regular curve in pieces, and P omega the union between C and its interior. Suppose that omega belongs to S. Then the following identity is verified.
The Green's theorem uses these two integrals that at the end it's the same. This one is the integral of the region C, that is the area of the curve, that it's equal to the double integral of the region omega, that is the area enclosed by the curve. This one is an integral of P in terms of x and y times dx plus Q in terms of x and y times dy. And this integral is the partial derivative of Q with respect to x minus the partial derivative of P with respect to y, and the limits of integration are given by omega, that the first integral, the integral that is most into the center, needs to have equations as limits, and the integral that is outside
the outside of the integral,
it has to have numbers.
Well, in order to conclude our investigation, now we are able to calculate the area of a region enclosed by a curve C using the Green theorem. So that is the mathematical principle that is the planimeter.